This is a square, made from cardboard. It has side length 10 centimeters, exactly the same as the one you have been given. Start by labeling the corners of the square A, B, C, and D, moving clockwise from the top left corner. Your first job is to choose a really appealing point on the side AB. I like this one, but don't copy me. Label the point you choose P. Next, locate the point on side AD that is the same distance from A that P is from A. Label this point S, and then make a straight fold from P to S, which creates a nice isosceles dog ear. Now locate the point on side BC that is the same distance from B that P is from B. Label it Q, and then make another isosceles dog ear by making a straight fold from P to Q. Finally, locate the point on CD that is the same distance from C that P is from B, and label it R. Now make two straight folds, one from Q to R and one from R to S. You should now have created a quadrilateral PQRS. The form of your quadrilateral will depend on the position of the point that appealed to you most, point P. Here is a variety of different quadrilaterals made by other people. But of course they are also, in a sense, the same, as they were made by following the same set of rules. Your job now is to determine the area of your quadrilateral and compare it to the area of the quadrilaterals made by your classmates. Who made the smallest one? By area. Who made the largest one? By area. Suppose whoever made the largest one wins a prize, a large packet of lollipops. Who is the winner? When you have calculated the area of your quadrilateral, write the value on the whiteboard so everyone can see each other's values and compare. Study all the values closely. Do you notice anything? So what did you discover? When we did it, the whiteboard was populated with these values. One student noted that there were a lot of mid-range values. What a nice observation. Another student thought that the values averaged out to be about 50 square centimeters. Another claimed that if P was placed in the center of AB, that the area of the quadrilateral would be 49 square centimeters. This idea was countered by a student who reasoned that if P was placed in the center of AB, the area would be exactly half the area of the square, 50 square centimeters. Oh, and obviously some of the calculation processes used were a bit dodgy. Also, maybe some of the measuring was less than accurate. So exactly what is going on here? To help your thinking, watch this animation that tries to illustrate all of the quadrilaterals that could have been made. Watch it closely and think about what is happening when P is located in particular positions. What, if anything, does the animation prompt you to think? Share what you were prompted to think with your class. Some students in our class noticed that if P was placed at the two extreme positions, to the very left of side AB and to the very right of side AB, the resulting quadrilateral, well, triquadrilateral fills half of the square, and so the area at each extreme point would be 50 square centimetres. That left us to wonder about the infinitely many possible quadrilaterals in between these extremes. What area do they have? More than 50? Exactly 50? Or less than 50? There are only three options. Of course, we also know the area is exactly 50 square centimetres when P is placed at the midpoint of AB. 50 here, 50 here, and 50 here. Could that mean that it is 50 everywhere? That seems like a very compelling conjecture. Your job now is to develop an argument that would convince the pickiest of people that no matter where you locate point P on side AB, the area of the resulting quadrilateral is equal to half the area of the square. It seems that the calculator thinks this is true. Team up with two people and give it a shot. How did you go? There is certainly more than one way to do this, but here is what I did. The folding of the isosceles dog ears gave me a sense of 1/2, because the triangle can be either outside or inside the quadrilateral PQRS. So here is how my argument goes. If I fold this triangle over and mark where point A falls, a point we'll call A dash, I can say for sure that A dash lies on the line PR, because angle APA dash is a right angle. I can also say for sure that the area of triangle APS is equal to the area of triangle A-PS, as they are the same triangle. Using the same idea, I can locate point B dash, which is also on line PR, and I can say for sure that the area of triangle PBQ is equal to the area of triangle PB-Q, as they too are the same triangle. Then I noted that line QR was the diagonal of the rectangle P-QCR, and so I can say for sure that the area of triangle QCR is equal to the area of triangle QRB'. Using the same logic, I can say for sure that the area of triangle SRD is equal to the area of triangle SA'. And most importantly, all of these deductions remain true no matter where point P is located. So since the area of the square ABCD is equal to the sum of the areas of the quadrilaterals AP-S, PBQB', B'-QCR, and SA'-RD, and half of each of them lie inside the quadrilateral PQRS, I can say for sure that the quadrilateral PQRS has area 1/2 of the area of the square ABCD, which is 50 square centimetres, no matter where P is located. And what's more, the truth of this argument does not depend on the side length of the square ABCD. As such, Following the rules for making a quadrilateral PQRS, when starting with a square of any side length, will result in a quadrilateral that will have area 1/2 of the area of the square. I wonder if you have a different way of arguing the truth of this result. If you do, share it with others and see what they think.